Howdy, my name is Luke Baber, and I am the project manager for our ESET 462 engineering project. And for this project, we made a 2-axis servo gimbal. So let's get into it. So first off, what's the goal of this project? So our goal is essentially to create a 2-axis gimbal that can stabilize a platform. This allows us, well, a little background on gimbals. Gimbals are generally used, a lot of them are used in photography now and in videography to keep, first, it's like a camera in a stable plane. They're also used in other parts of industry just to keep things mostly in a stable position despite external changes to the environment. So for us, we're going to create a 2-axis gimbal to stabilize the pitch and the roll. We're not worried about the yaw right now just because that's not as critical to the movement to keep a video camera smooth or a platform smooth. So 2-axis is a little bit simpler and also allows us to get the concept across for our closed-loop control system. So as I said, this will help demonstrate a closed-loop signal feedback for our control system. It plays off some of the topics and things we've learned in this class and allows us to just do a hands-on project to design a control system and just learn through that design process. So for our technical design, first let's cover the hardware. So here's a couple components we're using. So we're using Arduino Nano. It's a third-party one, so it's a little bit cheaper. We're using two MG995 servos. These have 180 degrees of range of motion, giving us plenty of room to move our our arms for our gimbal. We're using an MPU 6050. This is an accelerometer and gyroscopic sensor. It has both features built in. For our purposes, we're using the accelerometer to essentially track where our pitch and roll is going to be. For a gyroscopic one, you could use that to track your yaw, but like I said, in our case, we're not using that. For the wiring, we're using some 20-gauge wiring just throughout our gimbal to wire together all the chips and boards. For the frame, we'll be 3D printing it out of PETG filament. Going with color white is what I had. It also looks nice, so a little simple. For a power supply, it's going to be external, so it's just going to be one plugged in the wall. And we're using a 30-watt universal power supply. This allows us to have multiple settings on it, so it's like 3, 5 volts, 7.5, 12, 15 volts, so it's variable. For our uses, we're using it at 5 volts. Our system has been designed using Fusion 360. This is the model that I created. Up there on the top left is just a solid model showing kind of the structure of it, where the servo is going to be placed behind it. Inside, actually, our MPU 6050 gyroscopic and accelerometer sensor will be. You can actually see it also on the in the wireframe beneath it. And the wireframe kind of shows you a little bit of the insides of it as well as the overall structure and complexity that went into developing this. Alrighty, so for the other part of our technical design, I'll cover this software. So first off, we're using a proportional control system for our gimbal. So the way this essentially works is we start with our initial conditions, our initial homing point essentially for our servos. We collect an error measurement from that. Initially starting should be 0, so that'll bump us right into our readings from our gyroscopic and accelerometer sensor. From these, this will essentially change as the user alters the base. So the greater they alter the base, the greater the error measurement is going to be, which then feeds back into the servos, telling the servos that, hey, we need to adjust based off this error measurement we're receiving. So that's essentially how the system will work, is just constant feedback through our MPU 6050 sensor. And here's a simple program flowchart of how this looks like in our Arduino code. So essentially we start with our initialization. This initializes the pins that our devices are connected to, our I2C connections, as well as our MPU 6050 readings. The first several readings it takes in, it ignores those because sometimes they can be erroneous. So we take a couple readings in and wait until we're getting accurate readings, and then we start feeding that through the system. And as I stated before, essentially we just read in the readings, we take those values, map them into degrees for our servos, then we update those servos with those appropriate degrees, and then from that we go back to our sensor, take another reading. So it's a continuous cycle that constantly updates itself. Alright, here's a demo of our product. The first one on the left is just a video showing the first assembly, so I'll start playing that. So that shows just our 3D printed frame out of PTG. Like I said, we got some routing for the wires, so everything can be stored in the handle base there, and then this one shows it when it's fully assembled and working. So you can see as I move the base, the accelerometer picks up the position I'm moving it to and keeps the platform stable. Yeah. And it's also, you can see from the bottom, it's powered through the external power supply. And that's the gyroscopic sensor inside there. So that essentially stays in a level position and changes, I guess, in parallel with the user's hand as they adjust your system, and then that controls the servos. Alright, so for our costs, so this is just straight material costs. So first we have the Arduino Nano, our accelerometer. This is our MPU 6050. That costs $333. The servos we got in total cost about $19. Power supply and PETG filament. All these are taken into account. Total out to about $56. In terms of time cost, assembly is about 3 hours. There's a lot of soldering, assembly, and sanding of the 3D printed parts and stuff like that. Printing time, this was not straight, I guess, me working, but this was setting up the printer for me. Total combined time of an hour, but then letting it run and print the parts. Total time was 35 hours for that, and then for programming was about 1.2 hours. And in total, a little bit of money and a good amount of time, and had a cool project to show for it. Alright, so what do we learn in this? Well, for me particularly, it gave me a deeper understanding of what feedback controls are used for and how those are used to control your system appropriately. Our system is not PID, however, we use a proportional control system, so it's just like a P control system. A way we could have made it PID is by including the sensor, the MPU 6050, on the platform instead of the base. I also enjoyed the Maker Faire setting, giving us the option to make projects we enjoyed. And overall, the hands-on learning helped me reinforce the concepts I learned in class. Thank you for watching this video. I appreciate you taking the time, and I hope you learned something as we did on this project.